Okay. So for our final research talk, we're going to have Julio Parra-Martínez telling us about comments on dispersive bounds in the Swampland.
Okay, thanks a lot, Jake, and thanks to the organizers of this workshop for inviting me. I learned a lot. I had a lot of fun also meeting this community and just hearing what you guys are up to. So this was the title that I gave for my talk, but I thought that a better title would have been actually this, comments on S-matrix and the Swampland. And I'll be talking about some work that I've done with some of these people here, but I also want to make very general comments. And I think it's a good idea to kind of bridge these two communities. For once, we are like discussing all of these things about the global symmetries and the absence in quantum gravity, but and this is about a sector of topological operators and defects. But might I remind you that in quantum gravity, we don't expect local operators and like non-topological operators to exist either. And actually, the observables that we have are like asymptotic, like scattering amplitudes and undercorrelators. So at some point, we have to start talking. So why not now? And here are a few concrete questions that I think can start this conversation. And I think some of them we have answers to, some of them we are not, and we might be far from. But questions like, how much can a quantum gravity theory with a large gap differ from Einstein gravity at low energies? And can we use just basic principles to constrain theories and rule out theories from the bottom up? This would be kind of a bottom up version of the Swampland, just consistency, basic principles, unitarity, causality. How far can we go? And after we're done with that, how far is the Swampland? How much is there left of the space of theories which are seemingly consistent from the bottom up, but actually not really consistent, where we really will learn something from your guys' approach. Okay, so this is the outline. First, I will give a very short review of how we try to answer some of these questions. And some of you already saw my talk with Simone Caron-Roat on the Swampland seminar, so I will go pretty fast, but I just want to show some methods and then the results. And I'll just kind of say what I think we can actually do and we cannot do, and just throw some questions and some ideas at you to see where we could have some points of contact. And if I have time, which probably I won't, I have something else that might be also interesting. But yeah, okay. So the review, let me tell you what is the technology we use. So we use scattering amplitudes. We use really old technology, dispersion relations. So we take the amplitude, say if we have a scalar with a shift symmetry, we can consider it some integral of the amplitude around an arc at very high energies at fixed t, at fixed impact, a fixed momentum transfer. And based on some assumption about how the amplitude behaves at infinity, we can say that that integral is 0. And then by deforming the contour, we can calculate that by a little arc around the origin, which is computed in some derivative, effective field theory expansion, and then some integral along the cut. So this is the high energy, some integral along the cut, which is an integral of the imaginary part of the amplitude, which one can relate to the cross section in the forward limit when t goes to 0. And at low energies, this just will pick up some Wilson coefficient in the EFT expansion of the amplitude. And by drawing these relations, one can learn things like the coefficient of that operator of d phi to the fourth in this kind of theory has to be positive because of unitarity, because cross sections are positive, and it's integrated against a positive measure. Okay, and this is crucial for things like the proof of the A theorem in 4 dimensions, et cetera, et cetera. Okay, but this is a very general idea that we can use to put constraints on low energy observable, low energy effective field theories purely from basic principles. Okay, and so this one that I showed you is an example of these old-fashioned bounds that use positivity in the forward limit of amplitudes or cross sections, and the issue is that this can only bound signs of certain terms at low energies. Okay, so there's examples like the coefficient of f to the fourth in Maxwell EFT, or the coefficient of r to the 4 in gravitational EFTs can also be shown to be positive using some of these arguments. However, when we really want to turn on gravity, this can be a bit dangerous, because we know that there's graviton exchange in effective theory with gravity. Say, for instance, the leading term here for the 4-photon amplitude, that there's a 4-photon exchange in a graviton process. So we cannot really take this forward limit without having some singularity there. Okay, So we want to do something else. But before I tell you what we do, you might ask, well, okay, you showed some things about EFTs, but why would you think that some of these things can help us constraining theories of quantum gravity, right? Like all the arguments we have are about non-perturbative stuff, like black holes, some very serious things, not about computing amplitudes and perturbation theory. But I think I want to make a point that these dispersion relations are actually non-perturbative. Okay, there's some piece of the dispersion relation that can be computed reliably using an effective field theory, but the dispersion relation is a sum rule that relates things at low energies with things at high energies, and that high energy contribution contains everything, like black hole production, like your favorite non-perturbative process is going to be part of that. So secretly, we are inputting some of that in the UV, at least the fact that that should happen in a unitary in a causal way. Okay, and which are general and non-perturbative properties. Okay, so what is the modern form of this program of trying to draw conclusions from some of these conditions? So, for instance, let's look at the 4-graviton amplitude, and I'll go fast here. So it just has an EFT expansion. Okay, so this is some helicity configuration in 4 dimensions. Every independent coefficient corresponds to an operator in your favorite effective Lagrangian, and we have very simple assumptions and very basic assumptions. The fact that there's an EFT expansion, the fact that we have causality, which is encoded in the analyticity and crossing symmetry of the amplitude, Lorentz invariance at all scales, the fact that the spectrum is organized in terms of a mass and spin, partial wave unitarity, that the 4-particle amplitude has a positive expansion in terms of partial waves. So the spectral densities are like the couplings of the gravitons to higher spin stuff. And then some notion of Regge boundedness, the fact that the amplitude has to grow slower than s squared. And based on these assumptions, we can write a family of dispersion relations, which again is some arc at infinity that is 0. And it needs a certain number of subtractions based on how fast the amplitude grows at infinity. So it only grows slightly slower than s squared. And then we have a relation between low energy part, which is this arc, and the high energy part, which is an integral over a cut. And if we can find any operation that is positive on the high energy, even though we don't know what that non-perturbative contribution is, we can translate it into a property of the low energy coefficients. And of course, this is thanks to unitarity, the fact that these spectral densities are positive. Okay, so I explained this in a lot more detail in my Swampland seminar. But the reason why we can do something new with this is because we can find new functionals, not forward limits, but other operations that we can do that do things like as follows. Like if you take the leading sum rule is something that only receives contribution from G Newton and some R cubed coefficient at low energies. And at high energies, you have a sum over partial waves. Okay. So if we can find a functional that is 1 on Newton, that it's 0 on the R cubed contribution, and it's positive on all the partial waves, then we have a sum rule that tells us that all the partial waves have to add up to G Newton. Okay, and that shows us that gravity is attractive. Okay, no surprise, but also it tells us that all these higher spin states have to be weakly coupled. They have to couple weakly to the graviton. Okay, and this guarantees that every single coupling in my Lagrangian will be suppressed by G Newton, because I can always write a sum rule that relates, a positive sum rule that relates any coupling to these partial waves, which they're all suppressed by G Newton. Okay, and so this is basically proving dimensional analysis in CFT, in effective field theories, sorry, but actually finding what is the order 1 coefficient in front of the scaling in terms of the cutoff, which is always the mass of the first state. Okay, so that was a lightning review. Ask me if you have questions, because I went very fast, but let me tell you what we can do and we cannot do with this. So we can put 2-sided bounds on Wilson coefficients. This is in 4 dimensions, the coefficient of R cubed and R to the 4th, bounded in terms of G Newton. These are the coefficient of R cubed and R squared in higher dimensions. Okay, so this is technically more complicated, but note that these bounds are 2-sided. So for instance, if I turn off R cubed and I crank up R to the 4th, its Wilson coefficient cannot be greater than 12 in units of the cutoff. Okay. For instance, if you generated that using like integrating out some number of massive particles in a loop, this would tell us that you cannot have, for a fixed value of the cutoff, you cannot have an arbitrary number of massive particles. So this tells you that n has to be suppressed by m Planck squared over m squared with a known order 1 coefficient. In 4 dimensions, there's a logarithm. In high dimensions, this logarithm is not there. But this is essentially like an on-shell version of the usual species argument. Instead of using corrections to the propagator of the graviton, here we're using the 4 graviton amplitude. And indeed, we learned that the only way to have an arbitrary large number of particles is if the cutoff actually goes like 1 over the square root of n. Okay, but there's things that we cannot do. For instance, yesterday we heard about this positivity of the Gauss-Bonnet coefficient, and this is something that using these methods we cannot show that it has to have either sign to be compatible with unitarity, causality, etc. Okay, so that's something we cannot do. What else we cannot do? Well, we cannot extend many of these positivity statements when you turn on gravity. I told you that this T-channel pole is important. So for instance, the coefficient of this G2 coefficient, which was a coefficient of the 4 scalar interaction with a shift symmetry, that thing was positive by the argument I gave, but once you turn on gravity, it's not positive anymore. So this is in different dimensions, but one always allows a little bit of negativity. And so this is this T-channel pole that is entering, and that's actually a physical thing. It's not a technical issue. It's a conceptual problem, which is the fact that this pole dominates unless you make T very, very large. Okay, but we cannot make T arbitrarily large. So the largest that we can make T in the EFT is order of the cutoff squared. And the coefficient is always positive because gravity is attractive, or always negative because gravity is attractive, and that means that there will be always a slightly negative contribution to this sum rule. Okay, and unfortunately, the same thing holds for the 4-photon interaction. So there's this famous relation I didn't write in detail here about the shift in the extramality bound that would allow large black holes to solve to be the kind of candidate states that help us in satisfying the gravity conjecture. And there's several arguments for why this shift should be positive. But actually, I think that I'm missing a sign here. But it's been shown now by these people that if you apply this machinery, you cannot ever prove that the right combination is positive. Okay, so there's always, again, for the same reason, there's a little bit of negativity, and there's other assumptions that one can make and other arguments of why this should be positive, but dispersion relations, unfortunately, do not allow us to do. Okay, so questions that I think we should try to answer or to just explore. So here, I'm not going to tell you any result. I'm just going to say questions and comments that I have and what might be the issue or the challenges in trying to do some of these things. Okay, so can we quantify no global symmetries? Well, certainly we can write some rules for coefficients that violate some symmetry, which are like gravitational. For instance, if we had some Z2 symmetry, the leading coefficient that is only there with gravity, that we might be able to show that that has to be non-zero is this like a scalar R² operator if the scalar has a Z2 symmetry. And indeed, one can write some rule that tells you that this coefficient is given by some difference of essentially cross sections in 2 different channels of the graviton amplitude at high energies. Okay, the average over high energy states over these cross sections. Okay, so if one could prove that the right hand side is necessarily non-zero because of some black hole process, etc., then we would be done. But I think this is unlikely because from the point of view of scattering amplitude, it's very hard to tell if this Z2 symmetry is gauged or not. Okay, in the case if it was gauged, then this thing would be 0 and it would be perfectly consistent, but the amplitude doesn't know if the Z2 symmetry is gauged. Okay, so I think this probably is not the way to go. What about continuous symmetries? Okay, so for continuous symmetries, we do have a photon and we can tell if a symmetry is gauged or not, because but we have some charged particle, they will scatter through the photon, and the photon also has a T-channel pulse and photon exchange, but the amplitude grows with 1 power of s, with 1 power of the center of mass energy squared. Okay, and this is an issue because it's invisible in these twice attractive dispersion relations. I told you that the amplitude grows only slightly slower than s², and that means that we need at least 3 powers of s in the denominator in order for these dispersion relations to converge. Okay, So this is what we can prove in general, okay? That the amplitude has to have these general, or we have arguments like the chaos bound that tell you that this should be true. However, to be able to see the photon exchange and to tell the difference between a gauge and a global symmetry from a scattering amplitude, we will need to study dispersion relations with Fourier subtractions, like this one, which have a boundary term. Like the arc at infinity is not zero, is a number, which for a general theory of quantum gravity, we don't know what it is, but okay, maybe we can learn what this number is in some examples and see if we can make some progress. So related to that, what about if we want to prove something like weak gravity or like this repulsive force conjecture? So there's again a very nice single subtracted dispersion relation that always extracts exactly the coefficient that you want to prove some of these conjectures, because the force is nothing else that the value of the non-analytic part of the residue of the non-analytic part of the amplitude exactly at threshold. Like when the center mass energy is the sum of the masses squared, when S is the sum of masses squared, then we are exactly in the static configuration, and the 1/t-pole in the amplitude is precisely what the Fourier transform gives the usual interaction potential. So one can write a dispersion relation that extracts that residue. Again, it's singly subtracted. So we know how to find the right combination inside of the scattering amplitude, but you have to choose the external states, and I think in general we won't be able to prove that this has either sign, because we can just choose states that don't satisfy, like the states that are like not the ones satisfying weak gravity or repulsive force. And also we could always turn off the gauge interactions, and then we go back to no global symmetry. So if we cannot prove no global symmetries in this setup where we actually are considering scattering of the massive charge states, we shouldn't be able to prove weak gravity. Okay, still we have this nice sum rule that might have some use, but we need information about these boundary term. So here's a question for you. Is there anything universal about this boundary term in string theory that we can use to learn something using this dispersion relation? Maybe something about the High-energy point, if we assume that we are scattering the weak gravity states. Okay, what about other conjectures, such as the rank conjectures, etc.? So an issue that we have is that we can only bound some ratios of Wilson coefficients, but fortunately, the number of states that you integrate out typically shows up as a coefficient of some Wilson coefficient. So again, a question for you is, can one phrase these rank conjectures as an upper bound on some ratio of Wilson coefficients? Okay, so that's a challenge. If we can tell me that the Gauss-Bonnet number of like Carabi-Yau always shows up as the ratio of these two Wilson coefficients, maybe of some protected operators in some EFT that extends Sugra, then we might be able to make some progress. And otherwise, we won't be able to, at least today, because we cannot put rigorous upper bounds, like absolute upper bounds on Wilson coefficients. But there's interesting progress putting non-rigorous upper bounds by just writing ansatz amplitudes and seeing like what is the an amplitude, what is the nicest amplitude I can write, which is unitary and causal and has some value of the Wilson coefficient. And indeed, for instance, they showed that the coefficient of the R⁴ operator in 10-dimensional maximal supersymmetric theories cannot be too far from the value in string theory. Okay, and okay, so I think yeah. Okay, so okay, I have a few minutes, or how many? You started a bit. Okay, so let me tell you then something else. So this is the bonus. Here, I'll tell you that probably we are very far from connecting from these distance conjectures, but at least we start to understand how to think of amplitudes in a space of vacuum. Okay, so okay, everyone knows that our field theories are the scalars in the field theory are coordinates in the space of vacuum, but amplitudes are different objects because they do not depend on field basis. I can do field redefinitions, coordinate transformations, and this just changes my action by the on-shell condition. So this vanishes in an amplitude. And amplitudes are overlaps between states. So what are states? What are one particle states in over the space of vacuum, and actually they live on the tangent space. The usual wave function normalization one can take as a basis of the tangent space, and hence amplitudes are some section of some bundle over the tangent space of the space of vacuum. So I hear a lot about masses and how masses behave at large distances, but it would be interesting to ask questions about other quantities which are not masses. What happens when you approach some point in the space of vacuum, especially because it depends how you approach that point. Once you have a bundle, like the amplitude, it depends which direction you approach it, and we'll have one or a different value. Okay, so these are some examples of amplitudes. So amplitudes are just functions of curvatures in the tangent space, basically. And we also know how to move in the space of vacuum. So actually, we discovered a soft theorem that tells you that if you take any soft massless scalar in a quantum field theory, the result of the soft limit of this amplitude is basically a covariant derivative in the target space of the lower point amplitude. Okay, and if you have massive particles, there's a correction that makes sure that you stay on shell. The fact that you have 3-point amplitudes is the fact that when you move in the space of vacuum, your on shell conditions should still be respected. Okay, and actually we can show that this works when you couple scalars to essentially anything. Okay, so we know how to relate the amplitude at some point in the moduli space to some other point through these soft limits. However, even to move a finite distance, we always need to sum over an infinite number of soft emissions. Okay, otherwise we run into Zeno's paradox, which is that we want to go there, but we can only take half a step each way because we assume some hierarchy in the soft limits. And from this perspective, the distinction between finite distance and infinite distance from this point of view of scattering amplitudes is not obvious. So maybe one has to think about when does this theory break down? When does it become non-unitary to make some progress? Okay. Okay. So this is the summary of my talk. So I think what I show you by showing you that all these Wilson coefficients are bounded is that if you have a gap, it's the answer to one of the questions I had at the beginning, which is that if you have a large gap, then at low energies, the theory cannot differ from quantum gravity as you expect from a field theory. But now we know the order 1 coefficients. I also explained that some of the traditional suggestions of how to connect positivity bounds and some Swampland conditions are now understood to not quite work because of like precise physical reasons that have to do with the fact that gravity is attractive and that it dominates at high energies. And but I think it's still important to understand kind of what is the gap between this bottom-up approach to the Swampland, what is the space of consistent EFTs period, and the top-down Swampland, what is the space of consistent EFT that can be completed into quantum gravity theory. And so I think we should continue trying to narrow down the gap between these two approaches. And so yeah, I'm very happy to start this conversation, and I hope that that we will have many more, and that we can learn many things from each other. I think I'll stop here.
So do we have any questions?
Thank you, Julio. Very nice talk. Just naively at the beginning, you mentioned that you can prove that gravity is weak all the way out to the Planck scale. Could you expand around that?
Yeah. So what did I precisely mean by that? What I meant is that, so what are these partial wave coefficients here? They're the coupling of two gravitons to any higher spin state. Okay? So this is proven now that the coupling of two gravitons to any higher spin state is suppressed by G Newton. Okay, even above the cutoff, like these states live like these arbitrarily high energies. So this is a statement about the scaling with G Newton of that 3-point function. So it's always suppressed by a power of G Newton rather than suppressed by some other scale in your EFTs. Like, does it go like this amplitude? Does it go as 1 over some power of m to the n, or Is there a power of m Planck that one has to put in? So, of course, one can still have other 3-point functions in this theory, which are not 2 graviton, 1 higher spin state, which can be bigger. And in order to narrow down those, one would have to study scattering amplitudes of higher spin states and gravitons, which we can do. So this is just now a technical problem. How to do it? Conceptually, we understand now how to bound other couplings from the bottom up. And I think it would be interesting. It's just technically more involved because one needs to consider like partial waves for all of these things. Yeah.
Mm-hmm. But I still miss it. Why it has to be weakly coupled all the way to the Planck scale?
Yeah. Why? Oh, because otherwise one couldn't satisfy this sum rule. This sum rule is a positive sum rule that tells me that the sum of all of these partial waves, which are positive, with positive coefficients, has to add up to G Newton. So if any one of these partial waves was bigger than G Newton, one wouldn't satisfy the sum.
Mm-hmm. No.
In the presence of so this doesn't make any assumption about it. So here, all of these states are above the cutoff of the EFT, which is the mass of the first massive particle. That could be the first KK mode, could be the first string mode. It doesn't matter. Like all of those states couple weakly to gravitons.
What is the reference for that?
This paper that we wrote earlier this year or last year.
Okay.
Yeah.
Thank you. Thank you very much.
Do we have another question back there? Yeah.
Hey, thank you so much. Super nice talk. Can you elaborate a bit more? So I had several points, like for instance, for the moving in the field space in the bonus, you said it would be nice to have information about other quantities, not just the masses changing.
Yeah.
What quantities would you have in mind?
Like the couplings, for instance. The couplings is something that will show up in a scattering amplitude. And now they have indices.
Coupling of higher derivative terms necessarily, or any coupling? Like
no, even other couplings. Anything that is not a mass that shows up in a scattering amplitude. Now, in general, we have to be careful about how we approach these limits because many of these quantities actually live on the tangent space.
Okay. So, for example, because something that happens for us is that at infinite distance, like the gauge couplings decrease exponentially on the distance, while at finite distance decrease polynomially. So there is like a different behavior on the couplings as well. Okay.
Right. So I think that at finite distances or infinitesimal distances can be probed. But yeah, I think the biggest challenge is what I was saying here, which is how to think about infinite distance from a scattering amplitude perspective. I think we have no idea. I mean, we already have a hard time moving a finite distance. Yeah.
And for the weak gravity, just to finish, if I can, like you also put a question.
Yeah.
Yeah. Okay.
Yeah. So it's a very concrete question: is take your favorite amplitude in string theory for scattering of massive states which are charged, or in general just massive states. If we just want to put that charged under some global symmetry, can we say something about this sort of integral where we only divide by a few powers of the center of mass energy? And is there anything universal? For instance, is the sign of this thing universal in string theories? I think in a general theory, we don't know what this is. It's just a big question mark. But maybe a way to go about it is to just look at some examples. Yeah.
Okay, thank you.
Okay. I think in the interest of time, maybe we can thank the speaker and have more discussion after. Let's thank Julio.